two parts of the problem, right? All of you who are coming to this for the first time have to do two difficult things right now. Difficult thing number one is you have to figure out like how to run my crazy program. And thing number two is you have to figure out how to actually do your own research. And those are both hard. Well, hopefully the second one is the harder problem than the first one. But they're both kind of hard problems. And I like to separate them out somewhat. So I'd like to give you an example, a fairly straightforward example of a known problem with a known structure where you can get to the end and have a good fit without it being too complicated. But of course, nobody actually does research on something like iron sulfide. Nobody needs to measure beautiful XAFS data on iron sulfide and then go analyze the XAFS data and, you know, come up with it. I mean, there's no publishable result there, right? I mean, there's nothing, there's no there. It's a known structure. What everybody else works on are things that are obviously a lot more challenging than iron sulfide. So, clearly, whenever I wrote this talk, the days were different. So earlier today, I demonstrated Artemis by showing iron sulfide. So this let me start with the tool that takes crystal data and converts the crystal data into a list of atomic coordinates. That crystallography tool is just a tool. It's useful when, and there, look at that. I misspelled the word it's. How, oh, that's horrible. So it's useful when it's useful. If you have a crystalline material, awesome. Start with the crystal structure. If you don't have a crystal, then what? Well, you have to do something. So here I'm going to give you 3 hints about how to get started with non-crystalline materials. And the thing I want to say up front, the thing I want you to keep in your mind as I go through these 3 examples, is that the problem is actually simpler than it seems. Getting started on almost any XAFS problem is usually pretty tractable. It's usually not that hard. So here's example number 1. This is sort of the simplest example of something that's really not a crystal that I can come up with. And it's the difference between crystalline germanium and amorphous germanium. So crystalline germanium is obviously a well-known structure. Here's the crystal data. It's that space group. It has that lattice constant and a representative germanium atom at that position. You can run the crystallography tool in Artemis and expand this information into a list of atomic coordinates and go and measure the data that you measure using the structure on crystalline germanium and do everything that I did with iron sulfide, but do it with germanium. Amorphous germanium is a random continuous network, and that's an interesting concept. So amorphous germanium does not diffract, or it diffracts with just sort of, you know, this big, broad, sort of amorphous halo thing. But it's not really anything that you can get any structural information out of very easily. But it's pretty well known that amorphous germanium, this random continuous network, has the property that all of the germanium-germanium distances are about the same length as the germanium-germanium distances in crystalline germanium, except that instead of being a crystal, it's a random continuous network. But from the perspective of an XAFS experiment, it turns out they're kind of similar. So the question is, how do we get started on amorphous germanium, given that we obviously don't have structural information for amorphous germanium? Well, okay, one way that we can get structural information is to go to our molecular dynamics theorist friend and have that person run a molecular dynamics simulation and somehow use the output of that. So if we want to just do this simple problem, do we really have to go through all that work? Happily, no. So let's look at the data, because, you know, that's what you should always do first. You should just look at your data. So here's the Zanes data, and they bear a certain similarity. They both, you know, have a peak. The crystalline one has a bit of a shoulder there. but they both have sort of this structure here, and they both have this structure here. Basically, they look alike, except the crystalline one has more wiggles. If you go and look at chi of k, they look alike, but the crystalline one has more wiggles. If you look at chi of r, they look alike, but the crystalline one has more peaks. In specific, this first peak looks super similar between crystalline germanium and amorphous germanium. And this should not surprise us. If germanium is really a random continuous network, then we expect the near neighbor distance in crystalline and amorphous germanium to be about the same. So that this happens isn't surprising. So you can import the amorphous germanium into Artemis and import the crystal data for crystalline germanium into Artemis, run Feff, and drag over just the first path. Set up the simple parameters, much like we did for the first shell in iron sulfide, and parameterize it simply. And this is what I did after, like 2 or 3 minutes worth of work. I got to this level of fitting. And it's pretty reasonable. We got an S0 squared parameter of about 1, a reasonable E0, a delta R that suggested that the amorphous germanium has basically the same first shell distance as crystalline germanium because the delta R is really small, and a sigma squared that is the kind of sigma squared we expect to see in a real material. So this basically worked. What's the moral of this part of the story? We had an amorphous material, but there was something crystalline that was usefully similar. Right? We expected the first shell to be the same, approximately the same in the amorphous and the crystalline, so we ran Feff on the crystalline material and just used the first shell. So that's sort of hint or lesson number 1, is that you never know, again, you never know nothing about the material. We knew something about amorphous germanium, and we were able to run Feff on crystalline germanium because that's easy, right? It was easy to just convert the crystal data into a list of atomic coordinates. That was easy, and that gave us the Feff power to, the things we needed from Feff to make the fit happen, and the fit worked, it came out well, and it made sense. So crystalline analogs. Many of your materials you can use crystalline analogs. That's trick number 1. Okay, here's trick number 2. Trick number 2 is what do you do if you're measuring something on a molecule? Well, Feff, as I said yesterday, makes no assumption of symmetry or periodicity. We start with crystalline data often because it's an easy path to make input for Feff. That is, if you have crystal data, it's easy to turn crystal data into that list of atomic coordinates. But the point is that the input to Feff is not crystal data. The input to Feff is a list of Cartesian coordinates. That's what Feff wants. Feff doesn't know anything about an atom. It knows about a cluster of Cartesian coordinates. So, here's some data I took some years ago on some methyl tin chloride. So we had a couple of samples, dimethyl tin dichloride, which is a tin atom with 2 chlorine atoms. It's this sort of tetrahedral thing with a tin in the middle and 2 chlorines and 2 methyl groups, so carbon atoms out here. And monomethyl tin trichloride is just the same thing, except instead of 2 methyls and 2 chlorines, it's 1 methyl and 3 chlorines. The Zanes data look pretty similar. You see that there's some difference in chi of k, and you do the Fourier transform, and you see that there's, the first peak is somewhat different, and that must have something to do with the fact that one of them is 2 chlorines and 2 carbons, and one of them is 3 chlorines and 1 carbon, and that must account for the difference in the shapes. So I spent a little bit of quality time with Google, which is, sort of how we know everything these days. I don't really know how anything happened before Google, because we were all a lot stupider back then, apparently. But now we know everything because we can Google it. And I found a protein databank file, or that is, a file in the form of a protein databank file for this thing. In fact, it's the file that I used to make this ball and stick figure. I read this file into the molecule viewer, and it made me a picture that looked like this. Okay, well, that's what we need. This is a list of atomic coordinates. So looking into this file, we see that these three columns right here are the atomic coordinates of all of the atoms. And this column right here identifies which atom is at which position. That plus those three columns is essentially the information that we need for the input to Feff, because Feff needs a list of Cartesian coordinates. So I opened up a text editor, and I took this file and edited it a little bit to look like this file. You will notice that these three columns are verbatim the same as these three columns. I made a list, a potentials list, to identify the atoms the way that Feff needs them to be identified, and I made this column of numbers. The second one is the tin. First and third are carbon, then the chlorines, then the hydrogens. Wrong way. So tin, 2 carbons, 2 chlorines, and a bunch of hydrogens. So, and the rest of it is just sort of the boilerplate that I grabbed from some other Feff input file that I had lying around so that I'd spell all the words correctly. And I put in this information and cut and pasted this information. Now, notice a couple of things. The absorber is number 0. That's the definition of absorber in Feff. It's not the first item in the list. It's the one that's labeled as the absorber. So the absorber need not be at 0, 0, 0, and it need not be the first item in the list. When you do the thing to turn crystal data into a list of atomic coordinates, it puts the absorber at 0, 0, 0 and makes it the first one in the list, because that's the easiest thing for the human being to read, but the computer doesn't require that. So you can just do this, and it works. And then you can run Feff using this input file. You can just save this file to disk and import it directly into Artemis, run Feff, and carry on. And that's basically what I've done here. So here I have, so you'll see that the crystallography data tab is disabled. I imported the Feff file, and it's in that tab. I ran Feff, got the list of all the paths. The top 2 are the chlorine and carbon single scattering paths. And if you squint at these things, one for dimethyl tin, one for monomethyl tin, I just put these paths in and parameterize them, and I run the fit. So there was an example of something that is certainly not a crystal, but for which we have structural information. And you can convert that structural information directly into a Feff input file and carry on. And so if you have something that's reasonably close to your material, you run Feff on that, parameterize it to account for the differences, run a fit, and publish the structure of your material. So here's a little bit of an ad. There actually is, this could be done a lot better. So there's a ton of programs out there and a ton of different ways of representing structural information for molecules. And there's this interesting tool called OpenBabel that will convert input files for different kinds of programs. So different, it can convert the output of the Gaussian program, which is, so Gaussian, is that one that does DFT or molecular dynamics? I can't remember off the top of my head. One of those or both. And it writes an output file that has a list of atomic coordinates, and OpenBabel would say convert that into a protein databank file or the input file to something else. So OpenBabel is this interesting toolbox that converts atomic structure files one to the other. So you could imagine that OpenBabel could be modified to take any structure input and just write out the Feff input file for you, and then it could be integrated into Artemis. That would be really lovely, but it's something I haven't found the time to do. So if you or any of your students were interested in writing a little bit of C++ code, we should be in touch, because this is a simple thing that somebody could do to make a profound impact on the iFEF using community. So my last example is from this paper. And regardless of what you all do for a living, you should, if you do XFs, you should read this paper. This is a really clever paper. And Shelley is one of the real experts in this business of doing quantitative XFs data analysis. She's a really clever person. And this paper is great and explains this interesting problem where they wanted to understand how the uranyl ion, which is this uranium atom with two really short oxygens in the axial direction and 5 or 6 somewhat longer oxygen distances in the equatorial plane. So they grew a culture of B. subtilis, which is one of the common laboratory bacteria that people work on. And they brought that to steady state growth and squirted some uranyl acetate into the solution and let it come to thermodynamic equilibrium, and then asked the question, how does this thing bond to the biomass that was in the solution? And there's sort of only 3 things that it could possibly do. There really aren't that many ways that you could imagine the uranyl binding to the biomass. It could either be floating around still dissolved in water, in which case you wouldn't have any of these things. It would just be this structure floating around in water. It could bond to a carboxyl ligand in the biomass, and the way that the uranyl ion binds to carboxyl ligands in every example that's been studied is via this bidentate bond, where there's a carbon that's bound to the uranium with 2 intervening oxygens. Or the last really plausible option is that the uranyl ion binds to a phosphoryl ligand. And the way that always happens is that there's a monodentate bond between the uranium and the phosphorus with a single oxygen atom between them. And this kind of structure or this kind of structure are really the only binding options when you put this ion in the presence of biomass. The problem is that there's no way, well, there's certainly no such thing as like crystal data for this. I mean, this is a uranyl ion on goo, right, on like stuff. And there's, nobody knows what the structure of uranyl on goo is. That's just not something that you're going to find no matter how much time you spend on Google. So what did Shelley do instead? Well, she noticed that she went and looked at a whole bunch of crystal structures of uranyl phosphate minerals and looked at a whole bunch of crystal structures of uranyl carbonate minerals and noticed that basically every single uranyl phosphate has a little structural unit somewhere in it that looks basically like this, and every single uranyl carbonate mineral has a little structural unit in it that looks something like this. So she picked 2 of them that were relatively simple, triuranyl diphosphate tetrahydrate, and she found the crystal structure for that, and here's a ball and stick figure made out of that crystal structure. And she chose sodium uranyl triacetate, found the crystal structure for that, here's the ball and stick figure. These are big messes. But if we drill down into the middle, we see that this thing is full of structures that look like this. And if you look, you've got a uranium atom with a monodentate bond to the phosphorus atom. And if you drill down into this one, you see that it's full of units that look like this, where you have a uranium atom that's bidentate bound to a carbon atom. So this little snippet of this crystal is going to be used to represent this part of the possible binding environment for the uranium. And this little snippet right here is going to be used to represent the phosphoryl part. So that's basically it. She ran Feff on the uranyl phosphate mineral and took just the paths that include these atoms. Used those paths in the fit. She ran Feff on the uranyl carbonate crystal, took just these paths out of the Feff calculation, and used those paths to represent the contribution from bonding to a carboxyl ligand. She then also included a parameter in the fit that allowed the relative proportions of phosphoryl and carboxyl to vary as a function of pH, because at low pH, and I can't remember off the top of my head which way it goes, but at low pH, one of those two binding sites is preferred, and as you raise the pH, that binding site becomes depopulated and the other binding site becomes increasingly populated. And so she was able to show the pH dependence of bonding to phosphoryl and carboxyl ligands, not because she had some magic prior knowledge of what this thing looks like, but because she found crystal structures that had little units that she could snip out and put into the fit on the uranyl attached to goo. So what's the moral of my whole story here? The structure in Feff doesn't need to be perfect. Close is usually good enough to get started. And the example I just showed is a really great example of that. She clearly did not have a sample containing either of those crystals, right? Those two things were not in her flask of B subtilis in thermodynamic equilibrium with uranyl acetate. She did not have those crystals. That doesn't happen. But what she did is she found something that was close enough. Close enough meant it had little structural units that were similar to what she expected to find in her real sample. So the technical version of what I mean by it doesn't have to be perfect, close is good enough to get started. What I mean is, well, what I write here, that the small differences between how the uranium, oxygen, phosphorus atoms arrange themselves in the crystal compared to how they arrange themselves in the real sample, those small differences do not have a profound effect, we hope, on the calculation of F and phi, but the x-axis is sensitive to small changes in the local coordination due to the sign of 2kr term. So what I mean by close is good enough is that if you have a crystal structure that has that little structural unit that you're interested in, Feff is going to do a good enough job of calculating F and phi that you can use them in the fit on the unknown material. That's what I mean by close enough. That's the technical explanation of what I mean by close enough. So how is this done in Artemis? Well, import each crystal structure into Artemis. Convert the crystal structure into the Feff input file, run Feff. Line 3 is a little confusing because it refers to the old version of Artemis. But then you examine the path list, take just those paths that you think represent the structural unit that's actually in your sample, parameterize them and fit them in much the way that we did for the iron sulfide. So, the end result. What I want you to take away from this short little talk is close is good enough. To get started with Feff, you need to run Feff on something that is sufficiently close to what you expect to find in your sample, but it doesn't have to be perfect. In fact, if you already knew what your sample consisted of, you probably wouldn't be doing research on it. So this is the state we all find ourselves in, and we have to get started. Be creative. This is maybe the most important thing on this slide. So the difference between somebody who's really good at this and somebody who's just starting out at this is really the ability to conceive of a path from the beginning of the problem to the end of the problem. And the ability to conceive of that and see it through to conclusion is what makes an expert. So Shelley was clever enough to recognize that she could take snippets of scattering from those two crystals and use them to describe the structure that she expected to find in her real sample. And that's what makes her an expert. She was able to see that solution through to the end. So as soon as any of you come up with a clever idea for data analysis, figure out a way to solve it, and get to the end, then you're an expert. That's all it takes. You never know nothing. That doesn't seem like a very profound statement, but in fact it's an extremely profound statement. You always have some prior knowledge of what's going on in the sample. The prior knowledge that Shelley had in her case is that she had either phosphoroligands or carboxyl ligands. The prior knowledge that I had in the methyl tin case was, well, that it was methyl tin, and I could go and look up the structure for methyl tin. And the prior knowledge that you have in the germanium case is that a random continuous network, at least at the level of the first coordination shell, looks a lot like the crystal. So you never know nothing. And of course, remember that this is science and you don't get to know everything, but if you can figure out something about your data, you have made progress, and you know, that's how we go forward. So there is many answers to the question of, my sample isn't a crystal, how do I get started? As many of you as are in the room, that's how many different kinds of that question there are. Obviously, I haven't addressed everybody's problem, but what I hope I've motivated is that you can use whatever prior knowledge you have to get started, and any reasonable starting place is something that you can start to use to start poking at the problem to see if you can make some sense out of what's in your data. So hopefully that little talk helps you start to think about how to compose your XS problems. So any questions?
On the, I think it's the Feff input, and you've got the iPot.
Yeah.
Other than the absorber being 0, does it make any difference what 1, 2, 3 is?
No, they can be in any order. That doesn't matter. But you can only count up to 7 in Feff. Okay. However, in counting up to 7, they don't all have to be different. So in the case of the uranyl, it turns out that it's fairly useful. You have these 2 really short oxygen bonds. It turns out to be useful to make those a different potential from the oxygens that are a lot farther away. That turns out to be a slightly better model of the potential, because an oxygen atom at 1.8 needs to be a lot smaller than an oxygen atom at 2.4. And so you can have like 4 and 5 be the same element if you have a good reason for doing so. Yes?
To follow on from that, I'm afraid I've missed what iPot. I know you said it was the potential index, but what is that?
Yeah, it's just, right, so you have a list of Cartesian coordinates, but Feff needs to not only know where the atoms are, Feff needs to know what kind of atom it is. And so the 4th column is compared to this list up here, and that's how Feff identifies what atom is at each position.
Just a numerical identifier.
Yes, just well, tin has to be 0 because it's the absorber.
Yeah.
But other than that, chlorine, carbon, and hydrogen had to be 1, 2, and 3. But as he pointed out, they don't have to be in that order of 1, 2, and 3. They just have to be uniquely identified. Oh, and you can't skip a number. Feff is really unhappy if you skip a number. You can't do 0, 1, 2, 4. That'll make Feff unhappy.